So to restate the marginal principle, we need, in order to maximize net benefits or profit, the manager should increase the managerial control variable. In the current case, we're thinking about the quantity of output up to the point where marginal benefits equals marginal cost, or up to the point where marginal benefits is as close to marginal cost as possible. Okay, so at this point, you can't gain any more profit by any other change in the variable, the managerial control variable, because the marginal net benefits are zero. We've looked at this in the discrete choice case. Okay, now let's think about it in terms of a continuous case. And that brings us to Appendix A, where we're going to learn a little bit of calculus, just a little bit of calculus. And we're going to learn a little bit of calculus so that we can learn a lot of economics. Okay, a little bit of calculus goes a long way. And here's that annoying N for net benefits, where NB makes much more sense. Okay, so to maximize net benefits, a manager must equate marginal benefits and marginal cost. Okay, the objective is to choose Q so as to maximize net benefits. And with the benefit and cost functions, the marginal benefit is equal to what's known as the first derivative of the benefit function. It turns out the first derivative of the benefit function is the slope of the benefit function. Okay, so earlier we said that the slope of the marginal benefit curve should be just equal to the slope of the marginal cost curve. It turns out that the slope of the marginal benefit curve is the slope of the total benefit curve is the marginal benefit curve. And the slope of the total cost curve is the marginal cost curve. So to find those slopes, you can use some differential calculus. So the notation for a derivative is dB dq. So the first derivative of the marginal of the total cost function is dC dq, and that's the marginal cost curve. Okay, so when dB dq is equal to dC dq, or marginal benefit is equal to marginal cost, then net benefits are maximized. So a calculus class course would take you through a bunch of different types of functions and show you what the derivatives should look like. Okay. The only type of function that we're going to use is the power rule. Okay. The power rule is when you have a function, a dependent variable y, and the function is equal to a number a, multiplied by another variable x raised to the power of b. Okay, and the number a could be anything above zero or below zero. It can't be zero because if you multiply that, then a times x is going to be equal to 0. Okay, and the number b can be anything. Okay, so the power rule says that if you take the first derivative, dy dx, you take the exponent b and bring it down in front of x, okay, and take the product of a times b. And then for the exponent, subtract 1 from the exponent. Okay, and that would be the marginal or the slope of function y. Okay, so for example, let's say y equals 3x squared. Okay, so dy dx would be equal to 3, okay, a times b, so 3 times 2, which is the exponent, 3 times 2 times x raised to the power of 2 minus 1. Well, the power of 2 minus 1 is equal to 1. So anything raised to the first power means you don't multiply it by anything. Okay, so the slope of this function y is 6 times x. So the slope changes depending on what the variable y is. Okay, and the power rule can also be assessed with a constant. Okay, so since a constant is raised to the power of 1, okay, then the power rule just walks along when you have a plus or a minus here, and you just can do the analysis, take the derivative like you would. Okay, so 1 times c, and then the exponent would be we raise the power of 1 minus 1. Well, 1 minus 1 is equal to 0, so anything to the 0 power goes away. It's like we multiply c times 0. And so if we had a constant to this function, nothing changes. Okay? So we'll be using the power rule throughout the semester when we look at benefit and cost functions. It becomes very useful. The mathematics don't get much more complicated than this example. When we talk about cost functions, sometimes we'll see an exponent of 3. Okay, so in that case, if y was equal to 3, the first derivative would be equal to 3 times 3 raised to the power of 3 minus 1 equals 2. And this would be equal to 9x squared. Okay, so marginal analysis in action. So it's estimated that the benefit and cost structure of a firm is, and there's two functions there. Before we do that, let's think about, it's estimated that. Okay, these things are estimated with data. Okay, so what we're doing here is we're simulating a data-driven decision where we have already conducted the data analysis. And later on in the semester, we'll talk about how benefit and cost functions, or revenue and cost functions, like these examples, are generated from data. Okay, so let's say the benefit of Q is equal to 250Q minus 4Q squared, and then the cost function is just equal to Q squared. Okay, so the first thing we do is find the marginal benefit and marginal cost functions. So the marginal benefit function, okay, the first derivative of 250Q, Q raised to the 1 power, 250 times 1 times Q, 1 minus 1, so that's just equal to 250. And then the first derivative of 4Q squared would be 4 times Q equals 8, and the 2 minus 1 to the, so Q raised to the first power is just Q. So the marginal benefit is 250 minus Q. And then the marginal cost of Q is Q squared, so 2 times 1 is 2. And then Q raised to the power of 2 minus 1, Q raised to the first power is just 2Q. Okay, so net benefits are maximized where marginal benefits equal to marginal cost. Okay, so we can just set marginal benefit equal to marginal cost, so 250 minus 8Q equals 2Q. At that point, we just do a little bit of math. Okay, so the third line here, we've added 8Q to both sides. On the left-hand side, minus 8Q plus 8Q is equal to 0, so we're left with 250 on the left side. And then 2Q plus 8Q is equal to 10Q, and then if we divide both sides of this second to last equation by 10, then let's say 25 equals Q. So that's a more natural way of looking at that. And we might call that Q star. Whoops. Q star to indicate that 25 is the optimal amount of the managerial control variable. So that concludes the lecture for chapter 1. And at the end of chapter 1, Bay and Prince give you some hints on learning managerial economics. And they say one thing you can do is practice, practice, practice. Okay, so I'm suggesting you work the problems in the back of the chapters. And note that each is labeled with a learning objective. So we've specified the learning objectives for this chapter up front. And so you can find some problems in the back that fit those learning objectives. And I have provided 4 of those on As You Learn. So you can take a look at those 4, give them a shot. And if you have any problems with those, we can talk about it the following week. And another thing to do is to learn the terminology. Okay, and that's because if everyone knows the same terms and we all know the same language, and that helps economic practitioners communicate efficiently. So if we can talk amongst ourselves, and I can say marginal cost, and every time I say marginal cost, I don't have to say, remember, marginal is synonym with marginal is additional or incremental. If I don't have to say that, then we're communicating more efficiently. Okay, so there are key terms and concepts at the end, listed at the end of each chapter. Okay, so for the ones that we've covered, it would help if you became more familiar with those. And this would also help when you come to the exam, because on the exams, I will not provide definitions in the questions. I'll just say, hey, what's the marginal cost? All right, so that concludes the lectures for chapter 1.